Namaste and welcome everyone to the Programming Bootcamp session 2. I hope you all had a good weekend and some of you attempted the exercises. Those of you who have missed the previous live sessions, please note that the videos have been updated and I can see that the views are increasing. People are subscribing to the YouTube channel of transitional-ai Sydney. Thank you very much. Today we are going to go further into loops again with more examples and do some exercises. And tomorrow we are going to discuss more of the exercise 1. And I hope and request people to share their solutions so far of exercise 1, any of the parts, so that others can have a look. And also, if you do not want others to have a look, you just want some comments from me, then feel free to email it to me. Okay. So let me share my screen. Right, so this is the GitHub repo, and the session 2 is updated there, and not all the folders are showing because not all the folders have programs in there. Okay, so I will begin with the folder simple programs, right? And in simple programs, there are a number of programs here, and unfortunately, I did not really have the time to write them myself, so I referenced them from this website, and on all of them where I reference throughout the bootcamp, any exercise that I reference from other people, I will usually put the source, the link. And if there's no source or link, then you assume that it's from me. Okay. These are very standard programs and problems. So if you do a computing science major, usually in the first year, people take an introduction to programming course. And when I did it, I did all this in C++. I tutored programming later after I graduated in Java. And I was a tutor for introduction programming course. Then later, from Fiji, I moved to Middle East in northern Cyprus to follow Professor Christian Omlin, who was my master supervisor. And there he was teaching a course, Introduction to Programming, and some of the exercises, you'll see his name is there in the acknowledgement. He has helped me to develop this programming bootcamp. So some of those exercises, they were written for C. So we are doing it first time for using Python. And so then basically I was doing all these exercises and teaching all these things in C, not C++. C is a slightly different from C++, almost the same. And basically then later I moved to New Zealand, finished my PhD, then moved to Fiji. Then there I again attended these things in C++. I taught the class. I was a lecturer.
To start by offering my condolences to those families that lost loved ones overnight. You remain.
Sorry, let me mute everybody so that we don't get background noise. Please mute yourselves. That will be very helpful. And then, yeah, so this is a brief history of how I got introduced to these things. So this is the first time actually I am going over this again, but in a different programming language, which is Python, because I have not traditionally been used to programming in Python. I started in 2017, so I converted some of my code, and that's how I learned Python. But now it's quite refreshing to go over these things again. So you would see that in the folder there's this figure, and so we'll just begin with continue with the recursion. So last time we looked at a recursion where we were looking at the factorials, right? And recursion is a function that calls over itself, right? And so there's another example of recursion, which is with Fibonacci. And Fibonacci is named after Italian mathematician It has, you can see that it has links to, it goes back, why it goes back. Oh, yes. I should have highlighted, I should highlight Pingala at some point of time. So Pingala is a very interesting guy. He was a Indian mathematician more than 2000 years ago. The exact date, his birth date is not really known, but around 2000 to 2500 years ago in India. And he is the guy who came up with binary number system that we are using. And basically his name is lost in history. So somehow his name is appearing in this Fibonacci sequence, but we can read about this later. So and actually, all my projects in research projects in Bayesian deep learning, we are planning a library in Python, which will be called Pingala. So Pingala Bayesian deep learning library. That's what we want to get out in the coming years. There's a lot of planning and a lot of software development. So we will do it here at the transitional-ai group in UNSW. That's our goal in the coming years. Anyway, so this is the sequence. Similar to Fibonacci, you have similar to factorials, you have Fibonacci where it's iteratively developing, right? And there's a lot of things in nature that follows these patterns, and you can read about all that. I will just try to rush through because there's so many simple programs to examples to cover, right? So the base case in here, there are two base cases. The Fibonacci of 0 is 0 and Fibonacci of 1 is 1. Okay, so these are the two base cases. That means your program will start retaining, your function will start retaining things when it sees a number input of 0 or 1, right? The parameter is 0, 1. Or the Fibonacci of a number is the Fibonacci of n minus 1 plus n minus 2. So this is the 0 and 1. So this basically, it's very simple. I mean, it looks a little complicated here, but it's very simple if you look at the example, right? Okay. So the Fibonacci of this, let's say we are here, it is the addition of the last two. So that's the Fibonacci of 1. So 1 is 0 plus 1, right? The Fibonacci of 2 is the addition of the last two, 1 plus 1. Okay, the Fibonacci of 3 is the addition of the last two numbers. The Fibonacci of 5 is the addition of the last two numbers. Fibonacci of 8, addition of last two numbers. Fibonacci of 13, addition of last two numbers. Okay, I don't want to get you bored. Okay, so we can see a sequence here, and when there's a sequence, we know what we are going to do. We can either use a while loop, a for loop, or you can use recursion. So actually, in computer science, in programming languages, there are two major groups of programming languages. Okay, there's functional programming languages and non-functional programming languages, which are also called, forget what it is also called, but anyway, so the C++, Python, Java, all these are non-functional programming languages. Functional programming languages are Haskell, Lisp, and Scala. These are things, and usually in computer science there's a course about programming languages, and they are both the differences are similarities are covered. So Lisp is used mostly in graphic software development such as AutoCAD and others. And but yeah, the functional programming languages are not really used that much compared to the non-functional like Python. But what the reason it's called functional, because everything, all the loops are actually executed as recursion. So the while loops and for loops in functional programming languages such as Haskell and Lisp, they are all recursion, implemented as recursion. So So this is again factorial of a Fibonacci of 5 is, I always get mix these things up, is the 4 plus the fib of 3, and fib of 4 is fib of 3 plus fib of 2, and fib of 3 is fib of 2 plus fib of 1, and so on. So this is the base case here. These are the base cases here. These are the base cases here, right? So these two are just added. So basically, when you come here, this basically returns that. This basically returns that, right? And what do we see? So fib of recursion. Basically, we have the fib here, and the fib is calling fib again plus fib again. Okay, that's why you see the two branches of the tree. Okay, so because there's two function calls, and in each of them we are doing a n minus 1 and n minus 2, right? So this less than equal to 0 basically means if your fib is either 0 or 1, then you retain that. That means it is retaining 1 or 0. Okay, so this is what the Fibonacci is doing. And basically you could do things like, okay, let's print the fib of, so let's quickly run this, and fib of the first thing is I just did a quick call to that function here. I want a fib of 5. Okay, fib of 5, and basically the fib of 5, it says, is 5. Okay, so that's just the one function call. So it went there. So what happened was, okay, shall we do this? Okay, so we do it fib of 5. Okay, perhaps we could print what's going on here. Okay, let's see what it displays. Oh, too many things. Why? Let me just put, and Fibonacci is a function, is a, you usually, it works for positive integers. Okay, so that's why there's a check. So for fib of 5, you can see there's so many calls to this, right? And to see more, we could do n minus 1 and n minus 2. So to give us more indication of what is being called when. So you can see, and this so there's so many calls here, and you could take some time because I'll run out of time. I can't really go too much in detail, and try to spend some time on relating this fib to this, okay, to understand why do we get so many calls. And also in YouTube and all over the internet, you'll find a lot of examples about this. Essentially, it's a function calling itself. And then what else is being done? It's just asking, after you do that, it's asking for you to enter a number, and okay, for you to check. It doesn't ask to enter a number. We just want to check for how many items. So we want to find the Fibonacci of 10 items, right? And for each of those items, we print the fib. So that's why you use the for loop, and in the for loop we call the fib recursive fib function, and basically it goes there and it computes, it keeps recursing. So let's say if the fib was for 5, as we did here, we saw how many calls it did, right? So for fib of 10, for example, that would be a lot more. Okay, So let's just see, how many calls will be there for fib of 10. So it says fib of 10 is 55. But how many calls? You can see the number of calls is so much, the whole screen fits there, So basically what I'm trying to get is recursion is not useful in everything, but it depends where it needs to be used, So we go back and then let the fib of 10 be printed. So that's the fib or Fibonacci using recursion. And now we go into Fibonacci using iteration. Uh, so now for 10 items using the iteration, we see the Fibonacci doing it for iteration. And what is happening in the iteration is just, there's no function. It's just saying that the first N1 is the first two items, N1 and N2 are 0 and 1, and there's a counter. And basically you again ensure that it's a positive integer. And basically this says how many, asks the user for the input. And then basically it uses a while loop to implement this, right? And basically, as I showed earlier, that it's just addition of the previous two numbers. Those previous two numbers are being added, and the counter checks till for how many items we need to do this, right? So it keeps on doing that, and eventually what happens is the N1 is printed in this case. Okay, so essentially using a while loop, what is happening if we go back here? So we are using a while loop, and you can change that to a for loop as an exercise. Basically the last two, these two are given, and when you are here you just add the last two. When you are here you just add the last two. So that's what's being done using the while loop. So as an exercise, I need you to do two things. One is change above code using a for loop and implement a fib function to and two is develop a program which has both recursion and iteration function, right? So you develop similar to how we did for factorial, so that does for both, and then run experiments for large fib values and draw a graph. Okay, for values, and let's say just compare the time. So these are just two simple exercises to do. Okay, I hope you can try this. Now we move on to some other examples. So there is more while loops and for loops. We have an example called Armstrong number. And the definition of an Armstrong number, it's also called a narcissistic number, or somewhat of a narcissistic, another term for being a perfectionist, I would say. So the Armstrong number is the example is, let's read about this Armstrong number with some examples. So it's a narcissistic number, also PPDI plus perfect number, and that's the definition. And there are not many narcissistic numbers. Basically, in a large list, you have just some of them. And basically, there are some examples. And one example is of a narcissistic number is here. And basically, it's when you have this similar occurring, the same numbers, you add them together, multiply them, 1 times 1 times 1 plus 5 times 5 times 5 plus 3 times 3 times 3. So I don't have that much time to go over this, but let's run this quickly. So in the case where we have two, so you give it a lower and upper bound, and between them, basically, we want to find which are the narcissistic numbers, okay, between those two upper and lower bounds. So basically, we use a for loop, and in the for loop, we begin with the lower bound and we go all the way to upper bound, okay? So that means we iterate through using the for loop. Why do we have an upper plus 1? That's what I said. When you'll put upper, basically it will be always upper minus 1 as the end. So that's why you should use, the upper bound plus 1, right? So what is being done here? We just want to know what is the order of the number, okay? So that means if the number is, let's say, 100, then the order would be 3, okay? Why? Because it converts the number into a string, right? Meaning text, and then it just gets the length. So in this case, if the number was 2000, it would be 4, okay? So we begin with the number 0, and then we put what is the first number that we are checking if it is a narcissistic number, right? So the way we do it is, basically we have a sum is, your sum is 0, and we keep on adding to that sum. Firstly, the digit. So you take the digit. So let's say your number was, we started with, okay, let's say the number we did was 10, So 10, then because we started with a lower bound, let's say we came to 10, then your order would be 2, is 2, and you started with the sum, and now your temp is equal to the temp is number 10, something like this, right? And then you do a temp modulus 10. So 10 modulus 10 would be 0. That would be your digit. And you do digit to the power of order. Okay, so basically this is what's being done here. So the way we can see this working is you just say print. Let's do this thing for number, the lower is, because we know that Armstrong number is 153. So let's try to understand what's going on in here. What are all these values? So we do it for a very small case. So, okay, so we see these things being printed, right? So the digit 3, and then the sum is at the in the first iteration is 27, and the temporary is 15, right? So basically, by printing it this way and going it over and over again, you would be able to understand how this is actually working. Basically, when the sum value becomes same as the number, then we say that that is a Armstrong number. That's what when it is printed. So this value basically tests if it is an Armstrong number. Okay. Okay, so I'll just move on to another one. This is very simple. So when you have two values, it's just easy to swap them, right? On the table you have like um, you have a cup and a glass on the table. You can just swap them, and the locations change, right? But in programming, basically in the computer world, that is not so straightforward. Why? Because while swapping, you need to kind of track where it is in the memory. So let's say that we have two numbers and we want to swap them. The simplest one is so we enter the two numbers 15 and 12, and basically they are then swapped. So how it is swapped? In order to swap two numbers, you need to have a temporary value, right? You need to create a temporary variable to swap them. So basically what you do, you would placing the x that was entered, that was the 12 that was entered, for example, that goes into temp. Now your because now your y that was 15, the 15, that is overwriting the 12 of your x basically, and then whatever was in the temp, which was the 12, becomes your y, right? So that's how basically they are swapped. So the take home message of this is that you need to use a temporary value where you need to put the number, right? So it's it's important because we will see more examples about this in the next lessons. So the other one is a transpose, and last week we kind of saw an example of a transpose, but that was using NumPy inbuilt function, where you give matrix and basically you get the transpose. But how is that NumPy function implemented is important, right? And that NumPy function is implemented using two for loops, where you have to iterate over these two for loops to actually place this value that give the transpose of that value. So basically, yes, so you had 12, 7, 4, 5, 3, 8, and now you have it in this way, right? So you're just rotating it essentially. So in order to rotate it that way, firstly you need to create a memory of to place those values in, and that is called a result, right? And what is happening here in the result, we go into the length of x, um, uh, and this is your x essentially. And for each value of the length, so let's see what does the length of x actually return. Okay, so 3 is the length of x. So what is happening, because x is not is a list, and basically it returns the number of rows. Okay, this is not a numpy array actually, but we could do this in numpy array as well. So we have 3, so that means for each of those I, so we will go from I would be your 0, 1, 2. Okay, that would be the I. And basically what happens here, the 0, so you have x, then it will be 0, and the j would be in here, would be the j would be 0 and 1. Now because it says the length and it's giving the that, so that would be just 2. So this is 0 and 1. Okay, so what happens, the first thing is your I is 0 and your j is 0. Okay, right, both of them are zeros. What is happening here, so that means I is 0, j is 0 in the original one. That means you have this number 12 there, right? And what happens is, you in this one you want to put it here, the number 12, right? So basically you can see the major difference between the result is your j comes first and then is your I essentially, right? So for the 0 0, it's fine, both of them will be zeros, so you will place the number 12 there, right? But what happens when you want to do it for the next one? So let's say that the next one you are still at row 0, but column 1, and that's number 7. Okay, so that's number 7 there. So what happens to number 7? So number 7 is yes, 0 1 in here. The row is 0, the column is 1, and then it gets placed into, so it just gets placed into where the j is 1 and I is 0. So that means row is 1, so it gets placed into row is 1 and column is 0. Okay, so that's why you can see that the j, after the total, the j was placed that way. In similar ways the rest will be placed. It's just that you are changing the I and j position. So this kind of gives you the power of how a matrix, how you transpose a matrix. And it looks very simple when you are using a numpy array. You just call the t function dot t or dot transpose, np dot transpose. But now we can see how it's implemented. Okay, so note that like when it is a small matrix, then it's easier that you use these two double for loops. But the main reason numpy came about is because it has special ways to deal with operations when you have very large matrices. For example, you have like 1,000 by 1,000 or million by million. Then these two for loops doing it will, the time they in programming there's something known as time complexity. So time complexity is kind of a theoretical estimation of how many nanoseconds or microseconds the operation will take time. So whenever you have two for loops like this, the time complexity is n squared. Okay, if there are 3 for loops, 3 nested for loops, the time complexity will be n cubed. So n is the size of your matrix, right? So if your matrix was 1 million by 1 million, then the time complexity will be 1 million squared, you know. So that would become a very big problem because it will take long. And the other thing is then your operating system will have to juggle between memory, because a matrix size of 1 million times 1 million, to store it in your computer in the numpy array, it will take a lot of memory. It could be hundreds of megabytes to gigabytes. Okay, so those things numpy tries to resolve for you, but when that number becomes so big, then things become very difficult. When are these things needed? Why is this important? These things are needed in many algorithms, such as you know, in many machine learning algorithms, these things are used. So a lot of tasks that are done in computer vision, in machine learning, for example, face recognition, and many other algorithms, when your videos are being processed by YouTube, when YouTube, for example, is trying to recognize, you know, some components of a video, trying to detect if there's some components should not be there, things like that, filtering systems, then they all run algorithms, and those algorithms may be using that. And the more the pixels, the more, you know, the greater becomes your size of your matrix. And then all these computational issues take into account. So I just want to say, yes, when I was in my final year of my PhD, there was a new PhD student, right? I don't want to say his name, but so we were having lunch, and I was like, I was quite fascinated by Facebook back then. So, I mean, Facebook came about a few years. When did it come about? 2007, 2008, something like that, right? But this is 2012, and Facebook was growing in numbers, and probably 500 million people were on Facebook. Then he's like, we were talking about Facebook, and I was very fascinated from a computer science perspective, because Facebook is managing 500 million accounts. Then you have all these issues, you know, because the database, people are all loading, uploading, downloading photos and videos. How do you manage so many things? You have thousands of servers. How things are, you know, how this, there are so many programs built to actually make the things that we take for granted very to implement these things. For example, loading videos, photos, chatting at the same time. When we upload things, Facebook's also all videos or photos, usually they downgrade the quality so that the size of the photo is lower. So if you try to see that, sometimes, you know, you'll upload a 10 megabyte photo, and then you download that same photo, it will be a few hundred kilobytes. So there are algorithms running to do that. So yeah, my colleague or friend, he was like, oh, it's just a website. What is so fascinating for you there, you know? So this is what I explained to him. Then he's like, okay, right, from a computer science perspective, it's not just a website, right? Apart from the fact that it's connecting people, right? Okay, so there are other examples which I will just browse through.
Okay.
Any comments or questions? Let me just wait a bit and see if there are any questions or comments. Okay. So there are examples about the lowest common multiple.
So whenever he's been on sick leave, he has. Yeah, so he's quite honest about all of that.
Let me try to mute everybody.
From memory, I think mostly it's GP.
Right, better. So this example, actually the exercise is given there in exercise 1. So it's kind of a solution to the exercise 1. So I don't want to go over it right now. And the greatest common divisor, the exercise for sure, solution is there, but you're already implementing these ones. And swap numbers we covered, transpose we covered. Okay, so now let's move into some other examples of where loops are used. Okay, so one example is a bubble sort. Okay, so let's see what a bubble sort is doing. So one of the major problems in computer science, things that happen every day in the internet, on the social networks, is sorting, right? Sorting a list of numbers. Just as simple it sounds, it's quite a difficult problem, because when, as I said, when your list is a few hundred to a few thousand, that's okay. But if your list size is 500 million people, or now Facebook has more than 1 billion users, 1.5 probably, then to search for or sort users by according to something, let's say that the users according to their age, so every profile on Facebook has an age associated to it. And let's say that we want to find, Facebook needs to report to the government how many users are between, how many are teenagers, how many are adults, or how many are above 60. Then they will have to run algorithms to just do this very basic thing, right? So before you do make those statistics, you need to do the first thing first, which is you need to sort them, right? And so bubble sort is one of the worst algorithms out there in terms of time complexity, because its time complexity is n squared. That means that if you have a list of 100, then it is 100 squared. That's the time complexity, which 100 squared is 100 times 100 is 10,000. 1,000 squared, if the list is size 1,000, 1,000 squared is 1 million. So it is 1 million operations will be taking place, something like that. And if it is, yes, if it is a million or a billion, that's list size, then it will take too long. And usually we want solutions to just come on our fingertips, right? We want the solutions fast. So this is an example of bubble sort. The idea of bubble sort is that in your list, basically the numbers kind of bubble their way up. Okay, bubble their way. Let me refresh this page quickly, then it will start showing from the beginning. So here basically is a list, and you can see that how the numbers are kind of being sorted. They are bubbling all the way up. It's basically you take two numbers at a time and then check which one is greater, and then you swap them. That's basically what the bubble sort is doing. Two numbers at a time, and you swap them. And that is quite easy to say, but difficult to think about and to implement. So you can see there's 1 and 3, then it's swapping them. Then these ones, the 4 is already greater, the 5 is all the last ones have already been swapped. Okay, so now you have this. So there's another example. So you start from the beginning, 5, 6. You are trying to, then you go to the next one, swap them. Of course, you have to use the temporary variable that I showed before. Swap them. Swap. You don't need to swap because the 8 is already greater than 6. But now 6, 7, and 8, you swap them. 8 and 2, you swap them. And 8 and 4, you swap them. Okay, so you have now whatever is at the end, that's bubbled all the way through. So you have 8 at the end. We know that 8 is the largest. Then you come back to your list and start again. So, and you are not going to compare the last one, the last two. So the last comparison, you can just do this one, and now you know, because now you are not going to compare the last one. So that means as the last ones are done, your iteration in your for loop will be decreasing over time. So now your for loop, the last three ones are already bubbled and up, and you just need to care about the first five basically. Okay, so now you have the whole thing. So you can watch it over and over again. It's quite a good animation, and sometimes Wikipedia is quite useful for very basic algorithms. A lot of people contribute to it. So that was the example, and this is the implementation actually, right? So you have an, a function that takes an array, and that array, for example, is this one, just to test that function, right? And we want to call that function, and that function is called there. So, and you take the length by that, because this is lists, this is not numpy array. If it was numpy array, it will be np dot shape square brackets 0. That would give the length. So so the first loop, we go from the beginning to n minus 1, right? So whatever is the length of the list, 1 2 3 4 5 6 7 minus 1, and then you do you have another for loop, and you start with 0, right? You can see there, and then it goes to n minus 1, I minus 1. So this basically ensures the n minus I bit, right? That means for every I, you will do a for loop like this. Does not make sense, but I will show you. And if they are, if the numbers, the greater number, you basically swipe them, right? So this is how the swiping is done. The j and this j plus 1, but in here, this j plus 1 goes into j, and the other one j goes into j plus 1, which means that your 34 will come into the place of 64, and 64 will come into the place of 34. What is actually happening? How do we find out? We just try to print them. That's how you find out what is happening in any algorithm. Quite simple, huh? And I'm also going to print this thing just to see what are the values at every iteration. Okay. Oh, sorry, my spelling is quite bad in this one. File name, I will change the spelling later. It's Google sort. But yeah, so you can see the last one before the asterisk is 6, right? So there were all these operations happened. So it went all the way from 1, 2, 3, 4, 5, 6, 7, right? So 7. So it's going all the way from here to the end, let's say from to 6, because the index, it starts from 0. Okay, so 0, 1, 2, 3, 4, 5, 6. So it's doing some comparisons, right? So your I in the beginning is all zeros. Okay, so your I is all zeros. That was not a good idea. Just try to reduce the size so more things can fit. Right. So I is let's go back, 0, and then your J is 0, then 1 and 2 and then 3, then 4 and 5. So it is going all the way to, because it is 5, because the value of here this place is 6, but you don't, in the for loop you don't cover the 6, you will just cover n minus 1. That's how the for loop works, right? The last element is not covered. Then your I is changed to 1, and you're going from 0, 1, 2, 3 all the way to 4. Why? Because your this part basically is now 5. So you'll go from 4. Then your I becomes from 2, and then you're all going from 0 to 4, because 0 to 3, because this value becomes 4. Which, what this means is basically the end of the list, basically the last 2 values, these guys here, they are now kind of done, right? So let's just do one quick example. What would be the list? What would be the list when it is doing this? So it's just comparing 64 and 34, and then okay, the 34 is lower, so this 34 becomes like this and 64 becomes like that, right? And this is when your I is 0, and your J is going from 0 all the way to, your J is from going from 0 all the way to 5. I mean 6, but of course it traverses to 5. So this is what's going on here. So this, the first thing, your 0, 0, this and then the 0 and 1 is when basically there's going to be a comparison, and that's the comparison is being done, 0 and 1, and then that basically changes. Then it will be checking the 0 with, so first it checks 0 and 0, which it checks itself by itself. Of course, itself by itself, that's a waste, because there won't be any change, right? But then it does 0 by 1, then it does 0 by 2, right? So what happens here? What will happen? Because now your list is already updated. This is your new list. Okay. So 25, 12, 22, 11, 90. So after the swap, this is what's going on. And then on that, you are going to now do, you are at this position, and you are basically going to compare these two now. So what happens is, so yeah, that's 0, 1, and now you are doing it for 0 to 2. So 34 is being compared by 25. Okay. What I can do, I can also print these two guys here next to that. So then it becomes quite clear. what is being compared to what. Okay, so let's do this. So first, all these things are compared to 64. Then basically the list is updated. Then they are being compared to 34, and 25 is compared, all these things, and then so on. The list gets updated and updated, and towards the end, basically you'll see what you see is that towards the end only the smaller numbers are compared. Why? Because the larger numbers has already bubbled up. Okay, so this is an example of bubble sort. I don't want to take too much of time here. I think this much should be okay for you to have a rough understanding, and I would suggest you to spend some time trying to figure it out, just as I was just figuring it out. Okay, so there's another algorithm called insertion sort, and it works very much similar to bubble sort. You have a for loop and some sort of a for loop, which is like a while, which could be implemented as a while loop. So you have also a nested operation, and the time complexity is similar. So this I would ask you to do an exercise by implementing exercise, implement bubble sort and insertion sort as functions, right? Then for large list of values, so you should generate lists using random number. You can use numpy list, that's fine. Let's say if you have these size lists, you report the time and compare both functions. Okay, so then basically because in computer science, like every time you are generating, let's say you need to generate a list of 1000, and these are random values, right? Let's say between 0 and 100 in a range. Right, 0 to 100, and let's say you generated one, you did this, and you ran bubble sort, then you ran insertion sort, and you compared the time time in seconds or milliseconds, whatever the time function gives you. And that's just done once, but you need to do that 30 times. So if for each time you need to, so you will have a for loop where you go from run 30 experiments. So in computer science, in general, all the sciences, you need to do multiple experiments to kind of draw any strong conclusions about a phenomenon. And we want to find out which sort is better. And then there are other future exercises that you can do. It's not really part of this bootcamp. That is study, merge, and quick sort, and compare them with above. So you can do that. So basically, merge sort is one of the fastest, and there's a very complex operations it does, and its time complexity I think is n log n. You can check about that later. So it's faster than way faster than bubble sort and insertion sort. So okay, so that's sorting, and now we move on to something simple, but it is using functions. and recursion, and that's called a binary search. So if you're looking for some information or users, let's say Facebook by age, and you want to report number of users in a range, first thing you'll sort all the users by age. Then you can do things like search, you want to search for specific user, specific age category, let's say. That's how actually when you are searching for names in Facebook or Twitter, when you search for profile names, that's a similar thing is done. Basically, everybody's profile is sorted. It's sorted by name, not by the age, of course. And when you do a search, basically, so if the names are starting, if you're looking for somebody whose name is starting with B, right? If it is not a sorted list, then you will search from the beginning to the end of that list, and you are going to find B somewhere, right? But if it is a sorted list, then that name you are only going to search from the beginning to B, because it's sorted. I comes I, then there's B, then there's C, D, because it's sorted. Then you don't need to go to C, D, and all the way to Z. Okay, so that's an example of search, binary search. Basically, that's the idea behind binary search. Firstly, binary search works on a list which is sorted, and it can work on numbers, but it can also, so note that in the actual representation, all are the characters that you type in the computer, including your names. For the operating system, they are not actually names or alphabets. They are all numbers. So the number I, character I, so this is also an important thing to know. So this is the S key. It's the American Standard Code for Information Exchange. And that's what's implemented in the operating system uses this basically. So all the things here, like a backspace, horizontal tab, all of these have a decimal value and a hexadecimal and binary value. So all these numbers can be represented as binary. And actually, maybe we'll later do an exercise where this is converted to that, something like that, if we get time. So you can see that. But here you have these other things. So the actual representation for number 1 that we type in the keyboard, right, is the decimal value of that is number 49. Okay, a plus is 43. Capital A is 65, and a small I is 97. Okay, so that's the S key, basically. At the end of the day, everything is converted into this. It's a good way of thinking about things, like we do take things for granted, but for the computer, everything at the end is zeros and ones. And before it gets to the zeros and ones, the decimal number representation is used and it's then converted. So there's a big story behind these things. Okay, so there's binary search. So it says element is present at index 3. Okay, let's just do a binary search quick. I think there's also an animation about this. So, okay, this is the one. What do we see here? So is the figure that I was saying. So when things are sorted, like your number is sorted, yeah, a list is sorted. So basically you're looking for a number So what it does, it just takes that number that you are looking for. So for example, this is the steps. The number is, let's say, 7 that you're looking for. So it goes into the middle of the list. First, it goes into the middle of the list and finds if that number is higher than the middle or the lower than the middle. So the middle is there. It finds if the number is higher than the lower. So of course, now since the number is lower, let's say 7 was the number, it will not go the rest of the list, this list. It won't go there at all. It will just go here. To the first 5 of the list, right? And whatever is this list basically becomes your list, actual list now. That means the algorithm only considers the first part of the list. And in there, it will just look for the middle. But in this case, because our middle is, so how many numbers do we have here? 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, and 7 is the middle, and basically because it will look list here from here to here, then it will, at times the middle is not found, then it will be basically looking at the numbers that are close to the middle, and eventually it finds the middle. So let's go into the algorithm straight away. So in the algorithm, we have all that I was saying here. It's better said here. So it says check base case. So the base case is if, so we have two numbers here, high, low and high and x, right? So what we do here is we call the function binary search, and in that function we have to give the array, and we have to give what we are looking for, right, to that function. Okay, and then we have to give it the position where the value, lowest value is, and then the position of the highest value. Okay, which is 2 and 40, their position. So this is 0, 1, 2, 3, 4. Sorry, 0, 1, 2, 3, 4. So this first takes that array, and it takes 0, and it takes 4, and then it takes, so it takes the array, it takes 0, 4, and it takes the number that we're looking for, which is 10. We're looking for number 10 here. Okay. So now what we do, this takes these things, it goes here, then it tries to find, it checks a base case, and the base case is the high number is greater than equal to low. What it does, then it will get high plus low, and it will give them middle index. So we are all dealing with index here. We're not dealing with numbers at the moment. We're just comparing the high and the low, and basically we got the middle, right? Because if the high and the low is same, which means both of these numbers, if both were like 4 and 4, basically that part won't be executed, right? But now we know that the high, which is 4, is greater than 0. So what is the middle? Let's just print the middle. Oops. Right. So let's just run this first before printing it. maybe I made a mistake. So it says element is present at index 3, okay, when you run it. So what is the index 3? 0, 1, 2, 3. So at element index 3, you have the 10. Okay, that's what it is saying. But let's try to understand how this works. So there's not many operations that binary search will type, and it's a very efficient algorithm because it works on a sorted list. Okay, so there's binary search is supposed to be very fast. So the first things that it came up with 402. Okay, what we printed 4 high, low, and mid. That is high plus low, 4 plus 0 is 4 divided by 2 is 2. So that was the mid. Okay. So then it said, okay, if there's whatever the mid is same as x, then it will just return the mid. Okay. This is the case which is not going to happen right in our case. So that's the high low, and we are going to put this mid part there, and we say that, you know, so that we know that that's what it returns. Okay, so okay, so this part will be executed only once when it has found that, right? And that's what it did at the end. It found, we had the high, low, and the mid was 3, and it found in mid the 10. Okay, but this part will not happen right now. Why? Because this is not true. The middle value in the beginning is not that. Okay, so how do we know? We can just print this. How do we know what is the middle value? Because we were not printing the middle without checking it. Now we are printing the middle. So the first time around, the whatever was the middle value, that was this is what it found. It said, okay, this is the middle, 4 is the middle, and basically it checked if 4 is equal to 10. No, that's not true. So then it goes into your else if. And in else if, basically if the middle value, which is 4 that you have got, is greater than 10, is 4 greater than 10 because your x is 10 now, so this part won't apply. This means now the second half of your list is fully discarded. It will be fully discarded, these guys. Okay, but because this doesn't apply, then we are going into this one, and in there basically what is happening is we are taking the middle plus 1, right? Middle plus 1, and the high. So your low basically here becomes your middle plus 1, and the high is because you came with the high, which is changed now. You see your high now will be changed when you come here. Do you want to see? Okay, let's see. Please put in the chat if you understand binary search, then I can move on to the next one. Probably it's easier for you to get it, and I don't need to spend more time. So high, yeah, so that's the middle, and I will say this is in the else. Okay, so this is in the else. Any comments? We carry on. Okay, makes sense. Makes sense. Oh, great. Thanks, Hillary and Cynthia. So now we can see the else, right? So this means the else is done, and then in here, because then we kind of search, look at this part, and basically, oh, sorry, I was making a mistake. Sorry, this part of the list is going to be discarded, and then now basically we are looking at this part, and in there the middle is 10, and basically that's the index. It's using this. Okay, so to make maybe just in 1 minute I'll finish this. All right, so, and let's say if we were there, okay. So we're there, and we run it again. Do we see the else if? No, we don't see. Why? Because the 10 is there. So let's say we are looking for the number 3, right? So you can see the else if now comes, and then it's saying that the number 3 is at index 1. So that's basically the binary search tree. Okay, right. So this kind of ends the searching and sorting part. Okay, let's take a 1 minute break, close our eyes, take a little bit tea here, you guys refresh yourself, and then we will move into playing with again nested for loops to find the sum of a matrix. Okay, so far I've been just going over other people's exercise, so let's try to figure how things we can do ourselves. um, let's say that you read a file of numbers of file data file. You read a data file, and somebody asks you to find the sum in the data file, okay, of all the values in the data. So that is basically, I don't know what is going on there, but so that is basically a challenge, and anybody wants to say how they would go about doing it? How do you how would you find sum of a matrix? Anybody, any attempts? Right, okay. um let's go into the let's go into the previous lesson of nested loops, right? So which we covered last week, and here just a bit of a refresh. We used nested 3 for loops and nested 2 for loops, okay, and we we did create a numpy array and things like that. So let me just copy this and use this as a way to do this. Okay. So I have this function sum data, move into okay. Okay, so I just ran that function and didn't really give me anything much because there's not much. The thing is, generally, I suffer from memory loss, so it's hard for me to remember code, you know. And the other thing is like there's so several languages in my head, and it's just all mixed up. I don't know where to access what. So what I do, I usually build my programs by searching my previous code. There is a and there are two advantages of this: is I don't have to remember too much, and second is like I make less mistakes. So if I know that if for loop or nested for loop was working in my previous code somewhere, then I'll just copy it and start changing it, right? So that's what I do. So let's say that we want to call this function something, and we want to change the name. Okay, let's not call it nested loops. Let's say sum. What are we doing again? We're just writing a simple function that is sum of matrix that takes a matrix and gets the sum. Okay, so the first thing is we need to kind of make this matrix, and the way you make it is with the numpy, right? Okay, so we get this length width, and all these are done in the main. Please, you don't have to see how I do it. You can start doing it on your computers, and while I'm doing it, so it's the goal is basically this is more of a interactive exercise of building program, and those intermediate people, you can start working on your own screen. The beginners can continue watching. Intermediate and advanced users, basically we need a function that reports the sum of a matrix. Okay, so this is my matrix, and then I print my matrix, and then I call my function. Okay, I call my function sum of matrix. Why are we doing this exercise? I don't know, maybe it's just good to do it. The more we do, the better. Okay, or maybe it's going to advance your understanding of nested for loops. Okay, and of course you advance your understanding of functions. So okay, so these guys, I can bring them up out. So this is another matrix, that's 2D matrix, and this is a 3D matrix. Oh, by the way, I'm sure there are fans here of the movie Matrix. If you are, the good news that you may already be knowing, because fans do follow it, that the new Matrix will be coming out next year. I'm really looking forward to it, and I actually want to go and see that in the cinema. Hopefully by then we'll not have these restrictions that much. It's not a movie to see at home. Although I have a relatively bigger TV, than my laptop, but some movies you got to see it in the cinema. The last time I was lucky enough to see Tenet. Tenet was great. So okay, so we are setting things up here, and basically we have two matrices here. One is a 2D and one is a 3D. Okay, so what is happening here? We just take these things out because we don't worry about those things. We want to find the sum of the matrix. So okay, I'm not doing good programming here. Why? Because I told you earlier, and you should have stopped me, that compile, so and I can see that it doesn't work well now because so there's too many errors. Why? As I said, after every 3 lines we should compile. Okay, so let's begin again. Let's just compile the first 3 major statements. Okay, so right, so it's running sum of matrix. Okay, so that much compiled, and these 2 print matrices, let's say these compile. Right, so okay, good, that compiles and it printed things out. So it printed 3D matrix zeros, but I think it's better to have it initialized with some random values, the 3D matrix as well. So this both 2D and 3D, you can always get it from oh yeah, so it's a bit different when you do it. See the zeros, it was initialized, you can read it from a file, np zeros. So the np zeros, it was working, but when we try to initialize it with, we changed this, we were like, okay, let's do fill 3D matrix with things, then it gave an error. Why? Because the np random dot rand, it doesn't want the two brackets. Okay, so just note that when you are dealing with np zeros, then you need the 2 brackets, but when you are dealing with np random dot rand, you just need 1 bracket. Okay, so that's a numpy requirement. Some of us may not like it. We would want numpy to be more consistent in the way they do, but numpy is like my rules, my library. You want to use it, use it. Don't want to use it, go write your own. Okay, so that's what numpy told me. Okay, so now we have a problem. So we could print up till here, but now we have a problem. So obviously our problem is in the matrix function. Why? What is the problem? Let's try to understand this problem. Okay, it says name length is not defined. So is length defined? Oh, length is here. Why is it giving an error? Some of you may ask. Because length is defined for this, for the main function, and within the function you should have its own definition. Okay, so the thing is, what we want to do is make this more general. Okay, so we don't have to put length and define it, because we have the mat, and we know that the dot shape will give the rows, and the mat dot shape 1 will give the columns. Okay, so now we want to have the sum, so that means we need to define a sum function. So sum is 0. We need the right places to be indented, right here, ij, and basically whatever is the match let's just print the matrix. Okay, so that much we all know. Let's just print it. So okay, I'm playing by my rules, 3 lines. Okay, there's a 4th. Okay, sometimes we can compile 4 lines as well. So we have Matt, it's giving a problem. Why? Because I did not write Matt, I wrote Matt. Okay, so it printed all the elements. Note that you see it's not printed it in a nice way, like in a matrix way. Why? Because we have to use, I think it was /end or end, I forget. Then that will ensure that it prints it well. Okay, we can look at it up later. I think it was end. No, it just printed end. That was, I think that was given in the end part was given in basic loops or nested loops draw. Yeah, so if you look at the nested, oh, so it's just, this is what we want. So yeah, so this programming bootcamp can be a good resource in the future when you're developing programs, because you can always refer to it, the examples. Okay, and you use these examples. So at the moment, it's like, okay, so now you see the difference, right? So it was printing all in by rows, but now it's printing it this way. And if we do it actually, because it's a numpy function, you can just use print and it will print it. But if you want to go one by one, one by one, then this is the way you have to use the print. See, it was printing all this way. Maybe it's just you don't put anything. Okay, so now we can see that it's printed. And before we just printed this, because it's numpy, it just automatically prints. But what that print function does, it uses something like this. Okay, I don't know why it is saying none at the end. Okay, because it did not retain anything. But we haven't specified a retain value. Okay, so now we have specified a retain value. So that's the part where it prints, and we can take that same thing, and basically sum is very simple. We just keep on adding. Sum is equal to sum plus. Okay, so that sorted. So that's how a sum is. What is the sum? So this is the sum. Is the sum. If you want to see how the sum is being accumulated, so that's the accumulated sum over time. Okay, so it started with these values and it keeps on adding it to as it is going row by column to that. So this is just the sum. And let's say that we want to implement something where, let's say that we want to say that you only add the numbers that are greater than a number. So that means in this matrix, right, we only add the numbers that are greater than 0.2, right? So how would we do it, right? So that is sum, and we have another thing called, let's say, conditional sum, and that's the condition that the number should be greater than 0. I'll just take this out, just leave that in comment. Okay, so the conditional sum, so it's very easy. If so, because we want it to be greater than 0.2, we'll be like, okay, if this is greater than if it is greater than 0.2. So let's say we want to make it a nice program. So where the condition is coming from the main, and the condition is, so if it is greater than 0.2, then we are going to do this. So it's giving a problem. Why? Because I didn't indent it properly. Okay, so it's two very large variable name. It's not nice, but just for teaching and learning is fine. Nobody's checking. Okay, and so that's how it's going to be implemented. So what's the problem? Okay, let's just take this none out. System is matrix is missing something. Okay. Okay, so sorry, those more beginners, I should. So after the conditions are done, so now we have that the sum and so we have the sum and the conditional sum. Okay, sorry, those so the conditional sum will be always a bit lower than the sum. Okay, so that's how it's done. Sorry, those intermediate beginning users of Python, I should have pushed this all in the middle. So now it's all there. So we can do many things there. You can put it in, in the if statement. You can put other things. You can extend this to. So there are some exercises we can do. Okay, like one is implement function so that the sum is in between two values. So you have higher and lower value, right? Then another exercise 2 you can quickly do is extend this function so it can apply to to 3D, to matrix. So if and 1D list, So if it is 3D matrix and 1D list, this code will not apply to 1D. So what you need to do is basically here you said dimension is, at the moment the dimension is 2, right? So if your dimension is 2, then we are doing all these things, right? We are doing all these things. So we are doing all these things. So this part we don't really need, so I'm just going to put it out just for now. So, and what if the dimension is 1? That means it's a list. Then you will need to do a something like this. And you need to implement a kind of a I don't know if we can have a look at this dimension issue probably tomorrow. I wanted to go over something else. We have 15 minutes left. So that's one way. So if dimension, and if your dimension, so that's else if, and then else if your dimension, let's say, is 3, that means so then in there you need to implement the triple for loop, triple nested for loop. Okay, sorry, this should be, so you can do the same thing for when your dimension is higher. Actually there's a problem somewhere. Okay, so next we want to get prepared to, so we want to get prepared to look at our next assignment, our next exercise, and that's about a vending machine. And that's what you're supposed to start thinking about it after you attempted your exercise 1. And I'm sure that some of you have attempted, and some of you are quite well with it, and some are done well, and some are struggling, right? So, okay, the next exercise is vending. For the vending machine, we need to kind of start planning some things. Vending machine exercise, it's already out there in the exercise 2. So let's go back to the coins problem that we had. Imagine that we want to give the coins, and these are the coins that we implemented the last time, right? And the one that was quite easy to understand was this one, I think. So you ask the coins, and basically tells you how many of what, something like that. So what at the moment we are assuming, that we have abundance in the amount of coins we have. So we have abundant 50 cents, 20 cents, 10 cents, and we keep on giving it, right? But we know that in actual situation, the cashiers, they do not have abundance. Sometimes they run out of $1 coins. Then they will ask you, hey, is 250 cents okay? Right? And then you're like, oh, I don't want to take too many change in my pocket. And that has happened a number of times with me, actually. But yeah, the idea is that if you don't have the coins, what do you go? You have to give the next thing, right? So let's try to think how that can be implemented. So we have gone over conditions, we have gone over the basic loops, numpy, and all. So these things were done in week 1. So session 2, and we have the simple programs, sorting. We have done all these things, and now we need to do this coin simulation or cashier simulation. So let's add a file there called cashier.py. Okay, so we just put whatever we already had. I'll just take this much out so that, so basically in the cashier simulation, we are using our previous code. And so let's say 177 cents. Then it's saying, okay, 25 cents 3 times. Don't give any 10 cents, 5 cents. But what if we didn't have 25 cents? That's my point here, right? So the way we do it, we would be like, okay, we should have the number of denominations of each of these coins, you know. So let's have another. So let's say in there we have, 5 each. So we assume that the for each of those coins, okay, that is that much number of coins. It's very simple to understand. So the number of coins, we have 5 each. So in a very in a more realistic situation, we should have, the program should be taking into account the number of coins you have, and when it gives out the coins, then it should reduce the number of coins you have. Okay, and sometimes when you get money from the person, then it should increase the number of coins you have. Okay, so there's all these levels of things. So you're trying to simulate a cashier here, right? So, and of course, all these things should be done in a nice way using functions and stuff, but that's not the purpose of the class right now. You can convert this into functions. So basically, if we want to have restrictions of any kind whatsoever, we know we have to use an if statement. So to check if we have enough coins, we will have a if statement. But where does that if statement go to, right? So that if statement will go naturally in the for loop. Okay, that will naturally go into the for loop. So we are checking the amount, and then where is the place where we are giving the number of coins? We don't say that, we just appending that here in the results. So results is where we are giving the number of coins, right? So that means the updated number of coins after we give it out should be always what we have given out from our results, right? So your number of coins should be always updated by the results. Okay, so let's print the number of coins. Makes sense? So we're just trying to warm up, right? And in programming, when you are designing things, you need to warm up. So it sees this list cannot be done. You cannot separate it this way. perhaps why you need probably a for loop. Maybe yes, maybe no. Okay, let's just put a for loop. But if it was numpy arrays, then you could do it. I may be wrong, but it's okay to be wrong at times. And keep on experimenting. Keep on experimenting. So because you couldn't subtract those two lists, so I'm just subtracting it. So now at least our program is working. That after it gave those points, so that's the okay. It's better to do this operation after we print out. Okay. Then we updated our coins, number of coins stack, and the number of coins stack that we updated is that. Okay, so let me just push this for the newcomers so that they can pull it and start experimenting while I am doing this. Okay. So makes sense. So this is good. This is good. So far, so good. That means you got all this, you gave this change, and now you are tracking things. But we want to kind of implement something where we want to be sure if we need to give that change. So where do we do that? Let's brainstorm. Which line? Any ideas? Please put it in the chat. Which line should I change and put the if statement? Anyone? It's okay to be wrong. Just generating ideas here. Anyone? Okay. Actually, I also can't think about it right now. But let's try to think, where are we doing this? Okay, we do calculate the amount. We are doing this part, right? So we are checking the first, what does this do? Coin number, and that's what we print out later. Coin number is appended in the results, right? So that is equal to the amount divided by the number of coins. So we do assume that we have that coin, right? We do assume before we divide it, here we are assuming that we have the coin. We have the 50 cents, or we have the 25 cents. We have 5 of them. We are assuming we have it. What is my point is, what if this is 0 basically? What if we don't have the 25 cents? How does this work? At the moment, the program is saying that we are giving 25 cents, but we are not having it. We don't have that amount to give, right? So this is an example of how banks basically go, the financial crisis happened. They didn't have the money to give. So we could be checking it here actually. If the coins okay, so if the number of, we need to just check if we have it or not before we do this whole operation. Okay, let's just check if it is, we have it or not. So if that number of coins is greater than 0, so only if it is greater than 0, then we do all these things. If it is not, then what do we do? We'll figure that out later. Okay, so we are putting a if we don't have that, then it should naturally move to the next one. So it gave an error. So number of coins, which we have it here, list index out of range. Mhm. Print. Okay, we are running out of time. So I'll just leave. There's something like that that can be done. So I leave it to you to think, and then we end the session. So at the moment, basically, what it this bank Acacia is still there's something right happening that it didn't have that number of coins to give, so it just placed a -3 there. You know? So far it's not incorrect, but just not that smart to ensure that if you don't have something, don't give. Okay, so any questions? We'll continue with this tomorrow. Any questions or comments? I hope we are doing fine with these loops, and you are now more getting used to while and for loops, nested loops, and things like. Okay, thanks, Anthea. Things are going where it's supposed to go. We are slowly. We have in the last week, so we started Wednesday with very basic things, and then Friday we've covered some more basic things. And now today we are just looking at examples of those basic things. And tomorrow we'll continue with these, and then we'll think how these examples can fit up into a bigger thing, such as a vending machine, where these coins and change, all of these are given using functions and things like that. Okay. And tomorrow we'll try to see some other basic examples as well. So this is how we are going to go: concepts, examples, exercise, and sometimes exercise solutions. Okay, I will stop recording now and open the floor for any other comments.